review our semester-long data project for Data Science 620 under the instruction of Dr. Mahanama, our team, Nish Patel, Shashank Patani, Townsend Hurst. So picture yourself here. You're trying to figure out the best airport, best airline to be able to use, ultimately to minimize your delay. You're busy and you want to minimize that delay. So we originally set out to build a tool that could predict whether a departing flight would be delayed. As you can see here, we have our table of contents. I'll kind of walk through this throughout the course of this video. So as we really started to look into available data, we found that publicly available information from the Bureau of Transportation Statistics only reports arrival delays and only at an aggregated level, not by individual flight. So because of that limitation, we shifted our scope specifically to arrival rather than departure delays. And we limited it to only 4 airports within the state of Virginia: Reagan, Dulles, Richmond, and Norfolk, specifically for American Airlines, Delta Airlines, Southwest Airlines, and United. That was ultimately to limit the scope of the project. So as we imported the data, the raw data set included 21 columns, but our primary interest was in the Bureau's definition of a delay: arrivals of 15 minutes or more behind schedule. That's everything that's included within this data. During the exploratory data analysis, which we listed a lot of that down here in the unused section, we created box plots, line graphs, and heat maps to understand trends. Because the Bureau ultimately reports delays in cumulative totals, we initially struggled to compare these airports. So I'll scroll down here. Right here are some packages that we used throughout the project. But ultimately, because of that, we created a new metric, arrival delay per flight. And so that's this section right here, which you'll see periodically throughout the project. That allowed us to normalize the data and revealed much more clear patterns between airports and carriers, especially considering that we're looking at small airports like Norfolk and Richmond, but also big airports like Washington, Reagan, and Dulles. So once we normalized the data, we created heat maps, which showed consistent trends. Delays were relatively stable prior to 2020, in some cases not so much, but for the most part relatively stable, followed by noticeable increases afterwards, especially in the summer months. So right here is where we ultimately created those heat maps, and we separated it based on the airport, Norfolk, and the airline, in this case American. And so as you look at these heat maps, you can see the summer months, May through August, sometimes even extending into September, April. You can really start to see those delays increase, and this being after 2020. Now in some cases, like for instance Southwest, right here, you can see those delays really also were characteristic even before 2020 in some cases. But that kind of helped shape our understanding of the data. Now for the purposes of the presentation, I won't go through all of these, but as I kind of scroll briefly through them, you can see that we have at different airports and the different airlines. I'll click here just to take a look. And so, like I said, that shaped our understanding of the data, ultimately leading to our final import and regression analysis. So before moving into time series approaches, we attempted 2 traditional machine learning models, both the random forest and the XGBoost. Our workflow for this phase included combining all CSV files, cleaning missing values, one-hot encoding those values, and generating the aggregated delay metrics. And then I'll get to it here in a second, but splitting them into the training, validation, and test sets. So some of this stuff we had to kind of re-import just for the sake of getting it set and processed for these particular models. Here are those feature engineering that I just mentioned. And then right here, splitting it into the 70% train, 20% validation, 10% test subsets. And so that was kind of our first attempt to really try and model the data. Here we are actually training the models and then evaluating the models. So we got kind of an unexpected and unrealistically strong R-squared value of 1.0. This was our first clue that something was structurally wrong with what we were doing. After reviewing the inputs, we realized that the models were basically memorizing the cumulative nature of the data And because the Bureau reports monthly totals and because many of our features were themselves cumulative counts, the models were effectively learning a direct relationship, being that more flights equals more total minutes of delay. So in other words, the models weren't discovering basically aviation behavior, they were just reconstructing arithmetic, which is what we talked about throughout the course, especially within the model training, that you need good data for them to be able to actually train and test on. So because of this, we kind of took a little bit of different approach and basically refine our feature engineering. So now we kind of have this new section here where we went back to the drawing board and also took somewhat of a time series approach. So we went back, reloaded the data, and one thing that we did for feature engineering, we created this date column. Basically, the original data set stored year and month separately, and the year sometimes appeared as a float, which ultimately created this 2025.0 error. So here we fixed that issue, and then we added seasonal features here, both the month sign and the month cosine, given that, based on our heat map analysis, we realized that there were definitely seasonal trends throughout most of the data. So to basically avoid, treating these months as linear values, we encoded them in this way. Additionally, we created two targets, one for regression and one for classification. So regression, classification, and standardize all numeric features, while one hot encoding our categorical fields, such as the airline carrier. So from there, we went through some standard pre-processing of the data, and then ultimately using that regression, we did the random forest once again, now with some of those new features included, and then the classification and the forecasting here, we ultimately use, like I said, that Serimax model. So given that the previous model that we ran showed an R-squared value of 1.0, we didn't know exactly what to expect with this, but we were pleasantly surprised when we actually ran the report. Now, for the purposes of this presentation, I'm not going to go through the actual summary. I'm just going to go straight to the charts since we're on somewhat of a limited time. So going down here, our first model is going to be the model comparison, looking at the R-squared. And then we're going to look at the predicted versus actual. And then our third graph is that time series forecast. So as I scroll up here, you can see here our R-squared values, much more realistic, and for the most part pretty good, especially for DCA and Dulles. The higher values, 0.87, 0.91, a little bit lower for these airports, potentially because smaller airports, a little bit less data to work with, potentially less smooth out data, especially more driven by some outliers in the data. Here's the regression accuracy with that random forest model again, using the new the features that we included. And then here's one of the more interesting ones. Our Serimax model did a pretty good job for the most part. In some cases, it didn't predict some of the extreme delays, like you can see here for both Norfolk, Richmond, DCA sometimes in the summer. But at the same time, given the nature of aviation, sometimes delays like maintenance, air traffic control, like a model can't fully predict those kind of like black swan type events. So for the most part, it did follow a pretty good seasonal trend for all airports. So that's kind of everything that we included there. Thinking just next steps, conclusions. If we were to continue, we'd like to seek more granular data, especially at the individual flight level. And our end goal would ultimately be to be able to build a user-facing interface where basically a traveler can enter a desired date, airport, airline, and receive an estimated delay based on historical patterns. So we had a fun time with this project. I learned a lot about exploratory data analysis, data wrangling, model evaluation, classification, regression analysis, and we thank you so much for your time.